So, today I should give you an extra bit of information related to perturbation theory, and I would like to discuss two cases. One case that we'll finish today, and one case where we start today and then we are going to finish next Monday in 2 weeks. Okay? So as I mentioned before, I suggest you that you just work out on the theory. You pick up some exercise book if you want to train a little bit, but then in 2 weeks we will do exercise, and then I will assign you some very difficult exercise. Okay? I did not pass you the notes because in the notes there is a solution to the exercise. Okay? And of course I trust you that you are not going to read the notes, but it's better not to risk. Okay? So I will not give you the notes. I'll give you after you finish the exercise. Right? But of course, I mean. Now, in the previous lectures, I consider the case of non-degenerate perturbation theory. Right? Non-degenerate is required because you saw that in the perturbation theory, essentially, there were some denominators, and these denominators can blow if two eigenvalues coincide. Okay? So this is important also to give you some idea of what does it mean perturbation. Okay? What is the perturbation parameter? If you have a V, so we always write lambda V. Okay? But now just to confuse a bit, just imagine that the perturbation is V. V has the dimension of energy, right? So how can you decide if the perturbation is small or is big? Okay? Then we saw in perturbation theory that actually the terms that enter were something like matrix elements between two eigenstates, MVN, divided by the energy difference. Right? So in general you understand that the perturbation is weak is that if the various matrix elements between two different unperturbed states are small as compared to the energy difference between the unperturbed eigenvalues. And this is a good approach because both the matrix element MVN and the energy difference have the same dimension. Right? So this is, we just put lambda as a bookkeeping because to understand how we do the perturbation theory. But lambda smaller than 1 does not mean anything. Okay? Because what is really physically relevant is the action of the whole perturbation, lambda V, on the various matrix element, the contribution to the various matrix element, as compared to the various energy gaps, energy differences. So just please never try to say when lambda, so if my perturbation is lambda V, lambda much smaller than 1 is when perturbation holds. This is simply, it's not even wrong, it does not make sense. Okay? So you have to tell me lambda is much smaller, if you tell me lambda should be much smaller than some ratio between two energy scales which enter in the problem, then I can understand. But 1 by itself does not make sense. It's like saying that, you have a guy which is tall 2 meters and ant which is fraction of centimeter, and then you do a perturbation, lambda V, with lambda 10 to the minus 3. That probably this 10 to the minus 3 is a small perturbation for the big guy, but it's a huge perturbation for the small n. So I should decide what is the perturbation as compared to some properties of the system unperturbing. Okay? So if I do like this to a little boy or a big guy, this will have different effects. So the perturbation is defined as small when the scale, which is energy scale, whatever scale, is compared to a typical scale of the system I'm perturbing. Cannot be defined in absolute terms. I insist on this because this is pretty common mistake people tend to do. Okay? Now, there are cases in which if I do a perturbation, I may induce a situation which changes drastically the energy spectrum. Okay? And this is the case when I have, for instance, a degenerate spectrum. So a degenerate spectrum does not need to be all degenerate. Okay? Some part of the spectrum is degenerate. Also a few levels, so one, I mean, just so this means that when you have a complex system, a complex situation, if you analyze a part of the spectrum where there is no degeneracy, then you apply non-degenerate perturbation theory. If the part of the spectrum is degenerate, right, you apply degenerate perturbation theory. Okay? Now, let's make first a very simple example of what I'm telling you. Okay? So I would like to consider two harmonic oscillators. Okay? And then we just go to the perturbation theory. I would like to consider two harmonic oscillators, so which have h bar omega 1 a dagger 1 a1, okay, plus fine? Clear? This can be, for instance, an harmonic oscillator in two dimensions. If I take x and px and y and py, and I introduce, say these are, for instance, ax and ay, then I can write this way. Very good. So, what are the eigenvalues? So tell me, first of all, what are the eigenstates? How can I label the eigenstates?
With label 1 and 2.
And 1 and 2?
Yeah.
No, 1 and 2.
Yes.
Okay? So all the eigenstates will be n1 and n2. Okay? Now, I would like to know so what is the ground state?
A1 equals to 0 and 0.
Perfect. So the ground state is 0, 0. So the first excited state.
1, 0 and 0, 0, 1.
The first.
1, 0. Depends omega is smaller or omega 2 is smaller.
This is the answer. So it depends. Okay? So let's assume that omega 1, so just take omega 1 smaller than omega 2. Okay? So what is the first eigenstate?
1, 0.
1, 0. Okay? I just write first, you understand what I mean. Huh? It's 1, 0. Huh? The second?
No one knows. If omega 2 is way, way bigger than omega 1, it might be 2 and 0.
Very good. Oh, not way, way means,
Yeah.
what does it mean way, way?
Like smaller, smaller.
Okay, what does it mean smaller, smaller? I think I have an idea. It's not smaller, smaller, it's smaller than...
If omega 2 is, for example, 10 times omega 1.
No, I understand. So you're trying to do the easy path. So if omega 2 is 10 to the minus 55, then probably you're right. Now the question is that, how do I solve this problem? This problem has a solution, okay? Solve it. Not you, I mean, I'm talking to everybody. Because once I said solve it, all the rest relaxed. No, you have to solve it. Okay. By the way, did you copy the exercise or you did it yourself? So if you did it yourself without checking any book, then you did it well. If you copied them from the book, you did not well because there were small mistakes. And if you copy, then the two rules are, once you copy, first you have to pick up the right place where to copy. Okay? And second, you have to be accurate. So even copying is difficult. Okay? Now, let's solve this way problem. Let's call it the way problem. The way problem sounds a bit like Chinese word, way. So, tell me, how do you solve it? Back in the room, look at me and give me the solution. Now, you see that steering at there does not help. So you have to give me what is the criterion that you want. So what he said, way, is a good intuition, but then you have to translate in something concrete. You tell me, do this, I will do it, and then I will solve it.
If omega 2 is greater than 2 times of omega 1.
Very good. Now, it's not way, it's 2 or whatever. Okay, but how do you solve it? You do like this. You say, okay, I just take the eigenvalue 0, 2, okay? And this is h bar or twice h bar omega 2, okay? Then I say, I just take, I just take this. Huh? Then I take 2, 0. And this is 2h bar omega 1. Okay? These are the candidates, because if you solve the problem for this, for larger n, then, okay? And then you say, okay, is this bigger than this or not? So when omega 2 is larger than 2 omega 1, this is the second excited state. Otherwise, it's the opposite. Okay?
I don't get it.
So, the generic eigenvalue can be written like this. So it depends on n1 and n2, okay? And it is h bar So I forget about the 1/2, okay? This is just a shift, I don't care. So let's forget. I mean, I'm interested in understanding how to organize the levels. Huh? So this is N1 omega 1 plus N2 omega 2. Okay? Now you see that omegas are positive, N1 and N2 are positive, or 0. So the lowest value is when N1 is equal to N2 is 0. Okay? Then if I try to organize the various other terms, then I have to put, so for instance, here 1, 0, here 0, 1, then 1, 1, 2, 0, 0, 2, 2, 1, 1, 2, all this possible combination, right? Now, so now after 0, 0, then I will have E 1, 0, and this is H bar omega 1, okay? Then I have 0, 1, and this is H bar omega 2. Then I have E 2, 0, and this is twice H bar omega 1, right? But this is not just ordered in energies. I have to decide, so this is for sure smaller than this. But then I have to decide what is smaller. Okay? So if omega 2 is smaller than 2 omega 1, this is the right ordering. Otherwise, then I will have 0, H bar omega 1, 2, H bar omega 2, and then omega 1, and then H bar omega 2. Okay? And then if I ask you to do then you have to do all the rest. Okay? Now, is the spectrum degenerate or not?
Depends on omega 1 and omega 2.
So, the ground state is always degenerate. Okay? 0, 0. Then, in this case, if omega 1 is different, so if omega 2 is different from 2 omega 1, all these three levels are non-degenerate. If you take omega 2 equal to omega 1, then this is non-degenerate and these are 2 degenerate. Okay? Now suppose that, for instance, omega 2 is 4 omega 1. Then you will find out that there are a few levels which are non-degenerate, and then there will be, after a while, some degeneracy.
So can it be stated that if the fraction of omega 1 and omega 2 is rational, then degeneracy might...
Yes.
Yeah.
Yes. But this is an example in which there are some levels which are degenerate, some levels which are non-degenerate. Okay? I'm just giving this exercise, this example, because when you consider a problem, it's not that you say, okay, I'm non-degenerate and I'm degenerate, okay? You just take this, and if these two are degenerate, then if I ask you a question about the ground state, then you can apply a certain approach. If I ask something about here, you have to do something else. Okay? So within the same system, then it's the part of the spectrum that you are considering that makes a difference, not the problem by itself. Is this clear?
Yeah.
Huh? Exercise. Next week you will enjoy. So try to understand, okay? Just so try to understand how much you can learn about this, okay? So in terms of degeneracies. So for instance, take omega 1, omega 2, okay? And if I ask you, when omega 1 and omega 2, what is the degeneracy for each level? Okay? Then this consider this case, and then you take omega 2 equal 3 omega 1. And try to understand what levels are degenerate and what not. Okay? Now, when let's say now I consider a case in which I have some sector of the spectrum which is degenerate. Okay? I cannot do what I did before. I have to do something else. So first, I would like to understand what happened to the system when I apply at some subsystem degenerate levels when I perturb it. Okay? So when I perturb it, in general, what can happen that, so it may happen that, for instance, the energy of the subsystem changes its value, but the degeneracy remains. So suppose you have 4 levels which are degenerate. You apply a perturbation, the same 4 levels remain degenerate, but the energy is shifted. For example, I don't know. Or when you apply, did you ask a question? You can say it, don't worry. No, okay. If you in general apply a perturbation, then what can happen is that all or some of the degeneracies are removed. So in the previous example of 4 levels, you apply some perturbation. Then what can happen is that the 4 levels get different energies, or they become, instead of having one single level which are 4-fold degenerate, then you will have 2 levels which are 2-fold degenerate, or whatever combination. I don't know, it depends on so this is in general. Now let's try to understand what happened in perturbation theory. Now, when we talk about perturbation theory, this mechanism in which the possible degeneracies are lifted may happen at a certain level of perturbation theory. Okay? So it can happen already at first order in perturbation theory, or the first order does not work, you have to go to the second order, whatever, okay? So what I said before, it's true in general. If you do a perturbation, then something can change. So, for instance, in the previous example, if omega 1 and omega 2 are equal, tell me, do you agree that all the levels are degenerate except the ground state? Because when you exchange N1 and N2, then the energy does not change. Okay? Now, can you tell me why omega 1 and equal omega 2 is so special that all levels are degenerate? Is this related to some property of some symmetry of the?
Rotational symmetry.
It's a rotational symmetry. It's like you have two-dimensional with the harmonic confinement equal. So on the x and y, And then you have, right? So if you apply, for instance, a perturbation which breaks this symmetry, then you expect that the degeneracy is lifted. Hmm? So, for the degenerate, the situation is a bit more complicated, so we consider only the case in which the degeneracy is lifted in the first order. If it's not lifted in first order, then you have to apply in second order, but then the formulas become more and more complicated, so let's consider for the moment this. But it is important that you understand the idea, okay? Now, let's consider one single level, which is G, the G-fold degenerate. Okay? So if I have a single level which is G-fold degenerate, means that the energy of this level, let's call it E0. I'm checking if I'm using the same notation. I think so, yes. This is the unperturbed energy. And then associated to this level, I will have phi, 0, and alpha, where alpha labels the different eigenstate corresponding to the, so these are the sub-levels, say, okay? Where alpha goes from 1 to G. Okay? Now, you see that any linear combination of this is also an eigenstate. Right? So you just make a rotation of the basis, is still a set of states. Right? So, for the unperturbed case, then we don't know, we have the freedom to choose any basis, right? Now, what we would like to do is just to do the perturbation as we did before and see what happened. But we cannot do all the way as we did before, otherwise we encounter this problem. So let's assume, I'm assuming that, for simplicity, that the perturbation lifts the degeneracy. Okay? So if it lifts the degeneracy, it means that En will also depend on alpha. In such a way that at 0 order, then I will have only depends on n. Okay? Then I get plus lambda E1 n alpha plus da da da. Okay? So the 0 order does not depend on alpha, only the correction. Good. So you just substitute this into the Schrödinger equation. You stop at the first order, and then you get this equation. So the usual equation. So H0 minus E0 n by 1 n alpha plus V minus alpha prime. Here. Phi 0 of n alpha prime. Okay? So you see this term is 0 as before. But then what we get is something like this. Phi 0 of n alpha prime v phi 0 of n alpha is equal to E1 n alpha, and then I get delta alpha alpha prime. Okay? What is this? This is just an eigenvalue problem. So, diagonalizing this V gives you the first correction. So the first order correction to the eigenfunctions is found by just writing the matrix or related to the perturbation, diagonalizing, and this will give you the correction, the corresponding eigenvalue, the correction to the corresponding eigenvalue.
Sorry, I don't get the diagonalizing part. This is just matrix element of perturbation, right?
Yeah, but if you write as a matrix, this means that you have a big matrix. So you have to find the linear combination of. So essentially, what I said is, so I repeat. So this is a basis.
Yeah.
Okay. Now you can choose whatever basis you want. Huh? But you see that the basis that is selected by perturbation theory is that one which diagonalizes perturbation theory. So my question is that I would like to find what is the basis such that, I'll give you one example, such that the matrix associated to the perturbation is diagonal. And so the eigenvalues will correspond to the first order correction, and the basis is just the right basis.
So if I have like a degenerate problem, so I have to first or to normalize the states before doing this.
So you have to take a basis, okay?
No, because here.
So otherwise you cannot construct this. Is this the question or?
No, because in the last step, where you have this delta, you are like these two. I don't know. It's like if you were like assuming they are.
Okay, sorry. Let's try it. Let's write like this. Perhaps this is clear.
But they are orthogonal.
Yes. So can I give you one very simple example, and then we come back to this?
Yeah.
Huh? Is it okay? Do you have other question, or I propose I give you this simple example, and then we come back to this, okay? Unless you want to ask some question.
No, it's okay.
Huh?
No, it's okay. It's okay.
So this is a very simple example in which this procedure will give also the exact answer. Okay, but that's why I'm using this. Okay, so suppose that you have a two-level system. Okay, in which I write you in such a way that this is different from what you see, just to train a little bit. Okay, so I just consider this one. E0, 0, 0 plus E0, 1, 1. So the system can state in two states, either 0 or 1. You can call it whatever, left, right, up, down. It does not matter. If this confuses, let's write up, up, down, down. Huh? Okay? So tell me, what is the spectrum? The energies? No, just look.
It's
Look.
E0 double degenerate.
It's E0 and it's double degenerate because the particle can be in 0. So if I write as a matrix, this is E0 and E0. 0, 0. Huh? Okay? Good. Now, alpha up plus beta down. Is it an eigenstate of this Hamiltonian?
Yeah.
Yes. What is the eigenvalue?
E0.
Is 0. So you can take any linear combination, and this is still right. So in general, you can take any of two states, say psi1 and psi2, which are this and minus beta up plus alpha down, and this is a basis. Huh?
No, yes. This is like doing like Grant-Smith, like orthonormalization.
Yeah, you have to take a basis, okay?
Yeah.
So the basis should be orthogonal. The way you construct the basis, you can do. You can choose whatever you want. What I want to say is that you take a basis. Okay? Now, there is a zero order. Any of these bases will be an eigenstate. So there is no way in which if I do a rotation, then nothing happens. Right? Is this clear or not? I repeat the question because I did not hear the answer. Is this part clear or not?
Yes.
I'm not convinced. Okay, what is clear? Nadine is almost fainting down the floor. So, okay, so I would like to know what is clear, what is not clear. I don't think this is clear. It's body language. I see your face, and your face says, no, I have no idea what you're talking. This is written here. Huh?
I can choose any basis and the eigenvalue of the energy is always equal.
So, yes, this is what I said. And is it clear that what I'm saying? So if you have two states which are identical, so they are degenerate, any linear combination is also an eigenstate. So to form a basis, now, so the first part is any linear combination is also an eigenstate. Okay? Period. Then it comes to what he said, I have to find a way to construct a basis. So So I start from this state, then I use a method to construct an orthonormal basis, and then you get degenerate all the bases, right?
Can I have a question?
Yes, you can.
At this point, since the state up and state down are orthonormal states, they are degenerate. These two states that we made up with a linear combination, they are orthonormal and they are also degenerate.
Yes.
Why do we do this at all?
Okay. The next step is the answer to your question. Okay? So what I said so far is just to pointing out that when you see this problem, you tend to say that the eigenstates are up and down. And I'm saying no, any of this infinite possible solution is also a solution. Okay? So, as far as H0 is concerned, any of these choices are okay. You can choose because you like more up or you like more down, up plus down. You can do whatever you want, okay? So you can choose on the basis of calligraphy, color, symmetry, left, right, whatever. Huh? And all your calculations will be exactly the same. Now there is a perturbation V. And the question I would like to ask is that I would like to determine the first order correction. Induced by the perturbation. Okay? So my first goal is to find E1. Right? Don't think to the eigenstates, just think to E1. So I would like to also, because now I'm answering your question. I want to determine E1. Huh? Now, the answer to your question, and to all questions, look at me, is that out of these infinite possibilities, what is the best and only solution, not the best, the only solution of this type? Okay? Is the question clear?
No.
Now, the question is first that I want to determine E1. So far, any of these, sorry, I did a mistake. So let's call it this phi 0 and of 1 and phi 0 of 2, okay? But I have this freedom to choose this alpha and beta. Okay, so I just consider real if I have to, don't bother too much, okay? So I have this freedom. What is the basis that I have to choose among this infinite set of bases? Huh? Is there a preferential basis, or this question is wrong? Let's put it this way. I'm asking, out of this infinite possible equivalent solution for H0, is there a special situation, a special basis that will give me directly the first order correction?
Yes.
This is the question, okay? For doing this, so I don't know yet what is the choice. But if I plug this expansion here, I find that the solution, so the choice that I have to make in order to find already the first order correction is to take the basis which diagonalize the perturbation matrix. If out of these infinite choices, I took the one which diagonalized this matrix, the eigenvalues give me the first order corrections. This is the answer to your question. You may not like it or you may like it, but this is the answer. So if it's not satisfactory, you should tell now. Or shut up forever.
So, on the right side of the equation, the scalar product that we have written is delta alpha prime of alpha.
Yeah, because this is a basis.
Now, if we multiply both sides by another conical delta.
No, you have to see this as at the level of a matrix. Then
Yes,
you can
yes,
choose a representation. Let's say the following. You can choose a representation such that the matrix is diagonal. And when it's diagonal, then the eigenvalues are just the first order corrections.
But it's not necessary to go into a basis where V is diagonal.
If you don't go, you don't know what you get. No, in general, that's why I wanted to make an example. So what you do is the following. You choose a basis. Okay?
Yeah.
Whatever. Up and down.
Yes.
You write this matrix. Then you diagonalize. Once you diagonalize, you know that the eigenvalues are the first order correction. And the basis is the right one that you chose. Can I make one example? Okay? Let's make one example. And you will see that it's much more clear. Okay? I hope. Okay? Then I just add lambda v, which is lambda 0, up, down, plus lambda down, up. Huh? Okay?
Yeah.
Now, up, down is a basis. Okay? Then, so I write the next one, which is the right one, okay? But I write. So 1 over square root of up plus minus down is a basis. Okay? Now, if you look at H0, you can take this one or this one, it doesn't make sense. It doesn't make difference. Okay? Now, if you take this basis, let's take this basis. Okay? Then this basis is, so I want to write this, let's say, I write here, okay? So, H0 is, so I just use the up-down basis. Okay? If I use H, this will be E0, E0, lambda, lambda. I'm writing H, not HT. Okay?
Lambda V.
No, lambda V is just, these are the matrix elements, okay? So it's lambda. Now, try to write down this. So the H0 plus lambda B using this basis. Okay, so now if I write this U plus minus down, using this basis, Now H0 will be always E0, E0. Okay? So H0 does not change. Whatever basis you choose, you will get this. But now you write H. You do it, and then you will find that this is E0 plus lambda, E0 minus lambda, 0, 0. So in this case, you just diagonalize, exactly. Okay? So you see that there is a particular basis which diagonalizes the perturbation. Okay? So this means that if you choose up plus down and up minus down, then this is the first step in which these are, you lift the perturbation by just choosing a basis that diagonalizes V. So in practice, okay, now here the solution, the answer is the exact answer. But forget that this is the exact answer. This is what you want to do. In practice, what you do is the following. You just take V, okay? You just take one basis, whatever, just take this. V on this basis is 0, 0, lambda, lambda. Okay? You just diagonalize, and you find that E1 plus minus is plus minus lambda. The corresponding eigenfunction are up plus minus down over square root. So you see that at the first order correction, this plus E0 are the two eigenvalues, and these are the right basis from where you have to start. Is this clear or not?
Yes.
In this particular, this is a particular simple solution, a simple situation. So, sorry, should I repeat again? So, the procedure is the following. You have a degenerate situation in which you have any possible choice for the basis that you want to take. Huh? At first order, you want to find one of these bases which possibly lift the degeneracy. Okay? This equation tells you that you have to take the linear combination of phi 0 which diagonalizes the perturbation. If you do this, then you get the right basis that you want to use and the first correction to the eigenvalues. Okay? Now, an important thing is that in this particular case, already at the first order, the degeneracy is lifted. And so, the next step is to take this basis with this eigenvalue, and then to proceed on, you do non-degenerate perturbation theory. If the degeneracy is not lifted, then the situation gets complicated because you have to do an extra step. Okay, but since it's already confusing the first one, let's consider the first one. Now, let's do the following. Just consider the following situation, okay? So H0 is is 0 times the identity. Okay? So you have 3 states that I call 0, 1, and 2. Okay? And then I consider lambda v as lambda which multiplies 0, 1 plus 1, 2 plus 2, 0 plus Hermitian conjugate. Find the first order correction. I see that nobody wrote this example, so this means that you are not going to solve it. So at least you should pretend, or you should create the illusion that you are going to do it. Okay? I'm going to check what you are going to write, okay?